We're moving on to the last talk today. It's again great pleasure to introduce Dylan Possamaï, who will be speaking about contract theory and yes. Some politically incorrect.
Thank you, Kostas, for the introduction and the invitation. Okay, so, well, you will see this slavery part coming up a little bit later. So what I want to tell you about today, so this is an ongoing project that we're having with some of my colleagues in Toulouse, Anthony Réveillac and Stéphane Villeneuve. And that will be one illustration of this contract theory I've been working a lot on recently. But here, this is really going to be a modification of a toy model so that we can see what can happen if you in this literature try to make things a little bit more realistic. But before moving on to that, I'm going to tell you a little bit about what I mean by contract theory, and in this case this is going to be specifically moral hazard. Well, I have lots of time, so I will be able to spend a little bit more on this slide, which I usually go fast over. Well, this is a theory that started basically during the 60s and the 70s when economists realized that general equilibrium theory could not take into account asymmetry of information. And the problem is that asymmetry of information, this is absolutely everywhere in any relationship between economic agents. If you think about customers and producers, it's clear that the customer know more, for instance, about their tastes than the producer itself. Let's say that you're trying to sell cars. In your population, you will have different types of people. You would have people that love cars and that have money, people that love cars but don't have money, and people that don't have money and don't love cars, and people who don't love cars and don't have money. Okay? So if you have this, for instance, when you're selling this to someone, you cannot tell for sure in which type of the population he actually is. And of course, if he is rich and loves cars, you may be charging him a higher price with your car. Okay? So there is information that's missing here, and it makes this type of markets inefficient. The example that I was telling you about that comes from a very famous paper by Akerlof, A Market for Lemons, in this economics literature. And, well, you have kind of hidden information from the side of the consumers compared to the producers. You can also have asymmetry of information because there are actions that you cannot observe. The example that's going to be, like I'm going to look at throughout the talk, is the simple example of you hiring a manager to manage a project for you. And, well, unless you are behind the back of your manager all the time, you cannot be 100% sure how much work he actually puts into the project. Okay? His actions are not observable. The results of the actions, you can usually see them, but the actions themselves, you don't know whether the project is having a good value is because the economic context is great or because the guy has actually put work into this. Okay, so this creates frictions and externalities in your markets that cannot be taken into account by general equilibrium theory, because there everybody knows everything. Okay, so that started in the 70s from this acknowledgement that there was something missing, and, well, here we're going to look more about the situation of moral hazard. Moral hazard, as I was saying, this is the case where, because you cannot observe the actions of someone, he may be entering into, he may be making decisions that are not in your best interest, but there is no way for you to control this directly. Okay, so usually this is called moral hazard. And the main issue here is how to design optimal contracts. This is extremely vague for now. I'm going to tell you a little bit more what I mean by contracts in this setting. But basically, this is how to design properly the interactions that you have between the economic agents. Okay? So the way it usually works, this is a very simplified model, and that's actually the so-called Armstrong and Milgram problem. That's the first paper from this literature that was in continuous time. Before that, there was a huge number of papers in discrete time. I'm going to tell you a little bit about this later, why there is actually a very important gain by moving to continuous time here. It makes the problem much more tractable. Well, the typical situation would be the one where you have, which one? That's the one. You have just two important persons in the problem. One who's going to be called the principal, the other one is the agent. Principal is the one that wants the agent to do something. So he's basically hiring him or is entering into a contract with him. And he's the one that has more power because he comes with the contract and says, those are the terms, those are the conditions. Do you agree with this or not? So he comes to agent at time 0 with this. Agent looks at it, makes a decision whether he accepts the contract or not. And if he accepts, then the contracting period goes from time 0 on to time capital T, which is fixed. Okay? As soon as the agent has accepted the contract, he has to do something. Okay? And here doing something means choosing an action or an effort. And this, at least in this model, has an impact on this process X through the drift here. So just look at this rapidly. In this case, X, you could say that this is the value of a firm that I have given to you to manage. And, well, the value can change from two different, you have two different possibilities to make this change. You have this drift part that is chosen by the agent. That's how much work is putting into the project. And you have this Brownian motion here, which is noise. That comes from the economic conditions, and that can make also the value of X increase or decrease depending on what's happening. Okay? And if you have something like that, clearly, being the principal, if X is the value of the firm, you observe it. Okay? This is just maybe the value of the stock associated to it. So this is something that you can observe. But as Johannes was telling you earlier, if I observe X, even in continuous time, this is going to be extremely difficult to get back the alpha from the drift. The only way that you can have an unbiased estimator of this guy is if you observe this in continuous time with infinite frequency and you have a time horizon that goes to plus infinity. Okay? If you don't have this, then I'm going to have any estimator of this that I can find will have a bias that I cannot eliminate. So basically observing X does not give me the information that I want about alpha. So that's the asymmetry of information, that's the hidden action part. Okay, so what we're going to assume here is that the profits that the principal makes from all of this depends on X, which he observes, but of course I was telling you alpha is not there. So this is very simplistic situation. I just want, before moving on to the rest, give you a little idea about how much more general you can make this, because this you can have a lot of very different situations that can be covered by this program here. So this is the case basically of optimally rewarding your managers. Okay, so that's a situation that you would have in. Did I do this? No, I didn't touch my pocket. Okay, it's not me. So another situation you could be looking at, this is something we have worked on with Nizar Touzi and Yaksha Zvitanic. This is delegated portfolio management. So this would be the case where principal is an investor, agent is a portfolio manager. You go to him, you give him your money and you say, please manage my portfolio for me because I have no idea how the market works. Well, if you want to do something like that, you just modify your X here and you write it down. Does black work? Yeah, you can see it? Good. You would write this somehow, that would be the initial value. And here you would be having an integral. So this pi s would be the vector of your positions in the different assets in the market. And you would have, bear with me here, this is a vector, but I write it like that, d of st over st. That's the dynamic of all the assets in your market. Yeah?
Move the board a little bit on the right.
Yeah?
And I think you should stop it there.
Better? Okay, you would have something like this, and here instead of your control being alpha, your control would be pi. Okay? So that's a situation you can do with something like this. You can also look at electricity pricing. So that would be the situation where principal is an electricity producer and the contract is the contract that you have with a consumer. And what you want to do is somehow give incentives to your consumer to either reduce his overall consumption because you know that there's going to be a peak in the demand, so you would like the consumption to be less because you may not be able to face the demand, or more importantly, you may want to have your consumer trying to reduce the variability of his consumption, right? Trying to make sure that, if possible, he uses his dishwasher every Wednesday at 6 p.m. or something like that, because then you can estimate very efficiently what is going to be your demand later. Then in this case, X could look something like, I think the one that we have would be something like minus alpha t dt, that would be your control over the drift. And you could have something like sigma exponential minus beta t dwt here, and you have two controls, this alpha and this beta. Sigma would be a baseline volatility, and then you can choose beta positive to make it smaller, for instance. Okay? You can go to insurance problems. Forget about continuous time processes. Now say that X is a Poisson process that's counting the number of, that could be a number of default, that could be the number of times that you have an accident. Then you can try to decide what is the premium of your insurance contracts. That's going to give incentives to your insurees to try to make sure that if they can, they don't have too many accidents, and if they do have an accident, then it's not so bad on average. Okay, then it would mean, in terms of the Poisson process, that you would be controlling the intensity of the Poisson process, and you would be also having a control over the average size of the jumps associated to your Poisson process. Okay, it would be more than a Poisson process because jumps could be different, have size different than one, but that's something that you can put into this framework. Okay, so we have, again with Yaksha and Nizar, a very general way to handle those problems and to solve them. But this is not what I want to talk about here. Here I want to really stay with this model, which is the simplest one you can think of. I'm going to show you what the solution is, and we're going to see that there is a big problem with the solution, and then we're going to see what you can do to try to make something a bit more realistic. Okay. I lost something, of course. Thank you. Good. Okay, so this is the one we're going to be looking at. So now what is this contract I was telling you about? So here this is salary, okay? So we do something simple. You are working for me between time 0 and time t. At the end of the day, I see the results of your work and I pay you depending on what I've seen. So mathematically speaking, it means that the salary that I'm going to give you, this is something that you receive at time capital T, and this is measurable with respect to the filtration generated by X at time capital T, meaning that Xi is just any non-Markovian functional of X you can think of. Okay? So you observe whatever the value of X has been between 0 and T, and you give me a salary depending on this. So what does the agent do? Well, agent knows that he's going to receive Xi at time capital T because this is written in the contract. And knowing this, well, he's going to choose optimally his effort. And optimally means here, well, we're going to consider that the agent is a expected utility maximizer. To link this with the talk that you have seen before, I am taking something like that specifically because I want the problem of the agent to be time consistent. That's extremely important, otherwise most of what I'm telling you is not going to work. But here, basically, this is easy. I take exponential utility so that it's separable. This is what is going to make sure that this is time consistent. And the utility that the agent gets is whatever he gets from his salary here, minus the aggregated cost that he has, that has been incurred for him because of the work that he has done. And to make things easy, you take a quadratic cost here. Okay? So that's the simplest situation of this Armstrong and Milgram model. And I was telling you here in general, there is no reason why you would take psi to depend only on x at time capital T, because in general, you want to see the whole value, all the values of x throughout time, because you may be saying that, okay, it's great if x at time capital T at the end is high, but if there were a lot of variations before, that's bad for my company. So I may want also to keep track of this. Okay, so in general, psi is really non-Markovian here. Okay, I'm going to move a little bit forward. The optimal one is Markovian in this case, but that's really an exception. And that's because this guy here is, well, quadratic doesn't matter, but the cost function doesn't depend on time nor on x, and utility is exponential. If I change any of these, then most of the time the contract is non-Markovian anymore. But anyway, so mathematically speaking, what I have here is a time-consistent non-Markovian control problem. This is going to come up later, but if you know a little bit about this, you should be thinking that there are going to be backward stochastic differential equations that are going to appear at some point, and that's indeed the tool that we're going to be using to solve this later on. Okay, but that's the problem faced by the agent. That's not what we are most interested in. What we want to do is understand how, no, go back. What we want to do is to understand how this guy here can be chosen optimally. So I'm going to skip the next slide and move directly here. So what the principal does is that we assume that he knows everything about the agent. That's not a very good assumption. I'm going to come back to that later, but we expect that he knows that agent is exactly doing this when he gives him psi. So if you know that agent is doing that, then the problem that you are having here, this is a game problem. And what the principal is looking for is a Stackelberg equilibrium, because he's playing first. He says, that's the contract. Knowing the contract, he can compute the best reaction function of the agent, meaning here that he can compute the optimal effort, alpha in the problem of the agent associated to psi. And once he knows this, well, it uses a feedback optimization on the contracts, taking into account the fact that if he gives psi to the agent, then the agent is choosing the alpha star here. So forget about p star, this is just technical stuff with weak formulation, but basically this is alpha star that you have here. And the utility that the principal gets, well, to simplify, we also assume that he has exponential utility. There should be an x capital T here, sorry. So he gets utility from the terminal value of x minus the salary that he had to pay. Okay? So that's what he wants to do. The solution is here, but let's go back a little bit to tell you how you can actually derive this. So it seems complicated, and it seems complicated because you're maximizing over random variables here, so it's not something that's so nice immediately, and the random variable appears here, and it also appears in a very weird way at this point. So it's not clear immediately how you're going to do that, but somehow the plan is clear. The plan should be that for any psi, I should be able to understand what alpha star is, and if I understand that, then maybe I can try to solve this problem. So the first one is actually the easiest. The alpha star, well, you get it from BSD theory. Basically, you just do the same thing as usual. This is stochastic control, so you look at the dynamic version of the value of the agent, same as before, except that you do everything at time capital, at time small t. Because this is exponential utility, it's actually easier to work with the certainty equivalent instead of working with the utility itself, so you just inverse it. This is really because of exponential utility. This is a trick that has been known for a while in this literature. I would say that the first time I've seen this, it's in a paper by El Karoui and Rouge from, I think it's 2000. But anyway, so you just do this, you play a little bit with Ito formula, you use martingale optimality principle or dynamic programming, that's the same thing. And what you can show is that the certainty equivalent YA here is actually the first component of a solution to a BSDE that looks something like that. So if you can find, you give me Xi, then I can find Y and Z that solve this equation where the function f here is given exactly by the value that you have here. Then this characterizes exactly what this guy here, and more than that, the A star that attains the supremum in the definition of f is the optimal effort of the agent. Okay, so this is really, there's absolutely nothing new here. This approach to stochastic control problem where you have control on the drift via BSDEs, this goes back to El Karoui and papers by El Karoui and Keynes or Ramadan and Lepelletier, and if you want to even go back earlier than that, already in the 70s you have papers by Davis and Varaya where you have arguments that are extremely close to this, except that they don't talk about BSDs at all because that did not exist at the time. Okay, anyway, that's good for you because, well, you can prove that this equation always has a solution because this f here is quadratic in Z. It's purely quadratic, so it's very easy to prove that there is a solution as soon as this Xi here has sufficiently high exponential moments. So in this case, there is nothing complicated. Then you give me Xi, I can find Z. I have Y, which is the certainty equivalent, and this Z allows me to compute the optimal effort of the agent, which is just Z over C in this case. Okay? So using BSD theory, it's actually extremely easy to understand what's happening here. Now you're going to use that in the problem of the principle, and what's going to happen is that because you have exponential utility here, so X, you know what X is. X is, it's here. X is this, just now the alpha is A star, so it's Z over C. So I can replace X capital T using that. And then Xi, I also know why Xi is, because if you look at this equation, Xi is this at time 0 minus this integral plus this other integral. So what you end up having is exponential of a bunch of integrals with respect to dt and a stochastic integral. So the stochastic integral, since it's an exponential term, what you want to do is do a change of probability by Girsanov to get rid of it. And if you do this, you're going to have, you're going to have in this expression here, change the probability, and you would have the exponential of an integral with respect to dt. Take this integral, maximize with respect to z inside the integral, and that's the optimizer for you. Okay? Now instead of maximizing sur Xi, my Xi is basically characterized by the z here. So what I'm doing is choosing z instead of choosing Xi. And if I do this, well, I find that the optimal way to choose z is given by this ratio over here, and you can check that it's exactly what's optimal for you to do. So this z here is deterministic, meaning that the Xi, when you look at it, it's actually given as a constant plus this z star times xt. So what does it mean? It means that you have two components in your optimal way of paying your employee. You have a fixed salary, okay? This is something that you give him so that he's sufficiently happy. And then you have a part of whatever you're paying him that's indexed on performance, okay? And the way to interpret this is that this z star here is between 0 and 1. X capital T is the value of the project or the firm at time t, and the way I'm paying you is that I'm giving you a part of either the benefits or the value of the firm at time capital T. Okay, so that's something that's really easy to understand. The contract is nice in the sense that it's linear with respect to X capital T. It only depends on the terminal value. When you look at something like that, you're extremely happy. So that's one of the first reasons why this paper by Armstrong and Milgram is extremely well known. This is because the contract that you get here is extremely easy. And it makes the problem much easier than the one that you would have in discrete time, in the sense that if you take the model that I've given to you and you look at it in a one-period model, Okay, so you forget about continuous time, you just have something very easy. Now x is a Gaussian random variable with fixed volatility sigma squared. And what the agent does between time 0 and time 1 is choosing the mean, which is exactly what we are doing here in a more complicated way when I give you a diffusion like that. This is exactly what happens if you bring this back to a problem between time 0 and time 1. Well, if you try to solve this problem in a one-period model, well, there is basically, there is no optimal contract, because what you can prove is that you can define a sequence of contracts in this setting such that the value that the principal gets is the same as the one he would get if he knew exactly what alpha was. If he was the one telling the agent, you have to work this amount, which is the best case scenario for him, where there is no asymmetry of information. So in the one-period model, the problem completely degenerates. So what economists used to do with this would be like, that sequence of contract that you can construct is a bit weird, so it's not a realistic contract, so we forget about it. And the only contracts which are realistic are the ones which are linear. Now, if you restrict the contracts and you look only at the ones which are linear in the one-period case, the optimal contract that you get is exactly, previous one, exactly this one. That's exactly the same. So that's one of the success of going to continuous time in this paper, is that you have a very neat way to prove that the optimal contract becomes linear in the continuous time setting, and it has the exact same nice features that economists liked in discrete time. So, that was why this became very important, and you can see that there is, at least in this case, a very important gain by moving to continuous time instead of staying in discrete time. Okay, anyway.
Can I ask you something?
Yep.
Two things. First, the capital C you get from the participation constraint?
Yes. Which I didn't talk about, but yes.
Okay. The second is, this is in relation to the one period case that you said.
Yeah.
I guess, so the sequence of contracts that you find are very weird, you said.
They are not so weird, it's just that they are somehow, those are punishment contracts. If things are good, meaning if x is sufficiently high, I give you a constant. And if things are bad, I punish you a lot. That's what they don't like, because it's like punitive.
I understand, but mathematically speaking, could you get the same situation in continuous time if you let psi be more wild than just
if you don't
exponential moments?
Maybe you could have something like that. If psi becomes bad, the thing is, there is a one-to-one correspondence here between existence of an optimal effort for the agent and the fact that there is a solution to the BSD. So if you give me a psi that's extremely bad, here, it's easy to know exactly, like a necessary and sufficient condition to have existence of a solution. That's exponential moments. If I don't have this, okay, maybe I may have a solution, but in different spaces. So, okay, maybe you could have something like that, indeed. Okay, so this is extremely easy. Just a point. Of course, in the paper by Armstrong and Milgram, they don't prove this using BSD methods. This was not something that, the paper is from '87, so those were not things that were known. They have a completely different approach, which also works, but that's actually the only one that I can understand. This one is actually much easier to generalize in more complicated contexts. But anyway, so this is a situation where you're very happy, because as I was telling you, the Z star is deterministic, the contract is linear, everything is explicit, and it corresponds very well with things that you have known in discrete time. But the issue that you have here is that given how the contract works, it means that agent is participating into benefits, but it also means that it's participating into losses. Meaning here that if you look at the optimal effort, then under this x is just a drifted Brownian motion. So if you look at the value of x at time capital T, there is a strictly positive probability that it's going to be negative. And it can be extremely negative because it's a Brownian motion. which means that when I'm actually paying the agent, if the firm is doing very, very bad and it's losing a lot of money, I'm asking him to cover part of the losses. Okay? So I guess that if something like that is proposed to you, you're never going to accept, because as an employee of the firm, well, you should get money in the end, but if things are bad, maybe you don't get anything, but you don't have to pay yourself to your employer. Okay, so that's one of the big problems of a model like that, is that clearly you can have cases where Xi here is going to be negative, and that's not something that you want to have. So that leads to considering models where you have what's called limited liability from the side of the agent, meaning that you have to make him payments which are positive. Okay, that's an additional constraint that you put yourself, because this is more realistic. And if you do this, well, the way I've explained to you how this worked is becoming much more complicated than before. The first part with solving the problem of the agent for given Xi is basically the same. We're going to see that in a moment. The second part, playing with this exponential utility, now becomes more complicated, and you have to think at the problem completely differently. So from the point of view of the literature with this, limited liability in discrete time, it exists. People have looked at this a lot. From the point of view of the agent, there is one paper that I know of, and it's one of the most famous in this literature, the one by Sannikov in continuous time. I'm going to tell you about this in a moment. But I'm going to finish the presentation by telling you that actually with the way we try to tackle the problem, you can have, for instance, something that, okay, I'm not going that it does not exist in literature, because there are so many papers in the economics literature that it's sometimes tough to find everything, but I haven't been able yet to find one where you have both limited liability from the point of view of principal and from the point of view of agent, meaning here, point of view of the principal is that, so for the agent it's bad when X is very negative, but for the principal it's bad when, okay, so here Xi is equal to this, but what happens if the Xi that you get in the end is bigger than the value of the firm? Okay, so the capital that the principal has is basically the firm itself. So in this case here, what happens if you have a realization and this C here is sufficiently large such that this becomes greater than X capital T? Then you don't have enough funds to pay your employee. Okay, so you, in what economists say usually here, is that you have money somewhere else and you can complete. But you can also ask yourself how this would work if you have limited liability from the point of view of the principal, meaning that Xi has to be positive because you cannot ask money to your employee, but also Xi has to be less than X capital T because you cannot pay him more than what you have. And this is going to be extremely easy to treat with the approach that we have, and you can have more complicated constraints if you want. At the end of the day, this is always going to work the same way. Okay, so let's move on to this modified problem. So what I'm going to say now, as I told you, limited liability, meaning that Xi is non-negative. Now this is bad for principal, so I'm going to make him a little bit more happy, and I'm going to allow him to fire the agent. Okay? So if things are really bad before time capital T, I can also tell him, you're going to be fired. So what does it mean? Now my contract, this is going to be two things. If I want the agent to take his decisions, he has to know everything, so I have to tell him in the contract, between 0 and T, if you are fired at any point, this is how much you're going to receive. So that's the process Xi here. And I have also to tell him when he's going to be fired, meaning I have to explain to him what is the rule for firing. And the rule for firing here means that I'm going to give him a stopping time, tau, which is a stopping time with respect to the filtration generated by X, because this is the only thing that I know. And I'm telling him in advance, that's the rule. If this tau happens before time capital T, you're fired. For instance, tau could be, if X becomes smaller than a given value, you're fired. okay? This is usually what happens in problems like that. This tau is going to be the first heating time of some set by x. But I have to tell him right from the start how this works. So that's now the new type of contracts that you have here. So from the point of view of literature, as I was telling you, you can either see this as a limited liability extension of the model of Armstrong and Milgram that I've shown you, or you can see this as the finite horizon version of this Sannikov's model that I already mentioned and I'm going to tell you about, which is basically exactly the same thing that we have here, except that now there is no horizon capital T, so the contract can in principle keep going until the end of time, and he also has intertemporal payments, so you don't only have payments at the time where you're fired, you also get money before. But it's actually not too complicated to introduce that in the model that I'm showing you. Okay, so now you want to do the same thing as before in this case. Well, for the problem of the agent, that's the same. This process xi is given, tau is given as well. So when he tries to get his maximum utility, he's going to solve the same BSD as before, except that now time horizon is tau, and whatever he gets is xi tau. Okay, so here I should put tau minimum with t, but that's the same. Okay, so that's what happens. Now we want to understand a little bit more what is the impact of having this guy here being positive. So this is a salary. So if this is a salary, it means that I should have something that makes sense, meaning that the agent which receives this salary should have more utility than the agent which receives zero salary. Mathematically speaking, this is just a comparison theorem for BSDs, telling me that this is the terminal condition, it's positive, so the y that I have here is always greater than the y corresponding to the solution with xi equals 0. But if you go back to what I had before, when I take xi equals 0 here, since f of 0 is 0, the solution to the equation when xi is 0 is actually y equals 0, z equals 0, everything is equal to 0. So what you have here and what you can notice is that the constraint that you have on xi being positive, this is translated into a pathwise, not a pathwise, a path constraint on the certainty equivalent of the agent, which also has to remain positive throughout time. And this is just mathematically this comparison theorem, but it makes sense. It's just that if you want your utility at the end to be positive, it has to be positive all the time. Okay, so this is what I'm telling you here. So if you sum up what's happening here, you give me xi, which is positive, then the certainty equivalent of the agent is always positive, and I can find some process z such that I have this equation satisfied by xi. Now let's say that I want to look at the problem the other way around. Instead of taking xi, which is positive, I don't want to take psi, I want to take z. This is the same thing as I did before. I was telling you there was some kind of one-to-one correspondence between psi and z, and it was clear before. Now, because this guy has to be positive, it's a little bit more complicated, but you can still prove that, so this is what I was telling you, you can prove that the somehow converse statement is true, meaning that every non-negative payment psi that I can tell you, that I can give you, is actually the terminal value of a process that now I call yz. And what is yz? This is just this process, y, controlled by z. Okay? Now I'm choosing z, so this is a control. And I take as a salary the terminal value of this guy. So this is y tau now. But z cannot be chosen completely arbitrarily, as you've seen before. If xi is positive, if xi is positive, then y is always positive. So now if I look at this in a forward way, it means that I have to choose z such that y remains always positive. So what I have here is just I have to control my process Y using Z, and I have to make sure that it always stays positive. So it's a state constraint that I have now. And we actually know much more than that. Somehow, if you start here with something positive, then you take a control Z. What actually happens is that as soon as you reach 0, you kill the diffusion and you take Z equals 0 until the end, until tau. That's the only way you can make this happen. And economically speaking, it just means that when things are bad and the certainty equivalent of the agent becomes 0, well, I basically have to stop everything because otherwise I'm not sure that I'm going to be able to pay him something positive at the end. Okay? And that's actually what happens. One of the moments where you fire the agent, it's when the process Y that you have here, this YZ, reaches 0 for the first time. Okay, that's what you get at the end of the day, but you can already see it from here. So somehow now, what you had before was I can choose whatever Z that I want, which with sufficient integrability, and I take as a contract the terminal value of this forward process. Now the only difference that you have with the added constraint is that I have to take this Z in such a way that Y remains positive, so I have an additional state constraint. So works very well. And now why is it good for the problem of the principal? Well, principal has two things to do. He has to choose tau and he has to choose this process xi t. But now we know that choosing the process xi t is the same as choosing Z here, which is a control for this process YZ of capital T that I had here, and this is not whatever control that I want. It has to be such that this process remains positive. But now if you look at this is simply a mixed optimal stopping and optimal control problem with state constraints. I have two state variables, X and Y. I have one control Z. I have to choose Z such that this guy remains positive, and there should be T infimum with tau everywhere here, of course. And I have an optimal stopping problem here. But now this is something that I understand. I mean, if you know about stochastic control, this is not complicated to look at this and at least write down the AGB equation associated to the problem and try to play with it, which is not something that you could do before. Okay? So if you do it, well, since everything is exponential utility, you have a bit of scaling that appears here, so you know that your value function is going to look something like that. You can get rid of the state variable x that's here. You're left with this f, and if you do computations, you can show that the variational inequality that is satisfied by f looks something like that. So, well, that's not the most important part. You can do the computations. You can actually prove that there is that this guy is the unique viscosity solution of this. You can do better than this. We are almost sure now, the proof is almost done, that this has a C1 solution. It's probably not C2 in general, but that's actually enough for what you want to do. You just have to take care of the state constraint, and this is what you have here, because Y has to remain positive, and when you are exactly when Y equals 0, then you can check that what's optimal is to stop immediately, and that's it. Okay? So the good thing that you get here is that you have a way to understand how this works. You have to way to compute the optimal contract, because the optimal contract means computing this Z, the optimal Z here, and this is the one that you're going to get when you compute the Hamiltonian in the problem of the principal. You can get everything explicitly in terms of the solution to this PDE and its derivatives. Okay, so that's good. And this is something that's extremely similar to what Sannikov has done in his paper. It's just a bit more general, because in our case, principal can be also risk averse. Okay, but that's not what I want to talk the most about. So that's the way to do this. You actually get a lot of insight into the problem by just looking at this PDE and the way we do it. And one of the important findings that you have here are the following. So the first one, and we have the same. One of the good things about this paper of Sannikov, this is something that I didn't tell you, but So agent has a participation constraint, meaning that he's not going to accept the contract unless he gets a sufficient amount of utility right from the start. Okay? So this is the so-called reservation utility. And in the model of Armstrong and Milgram, you always give him exactly this. So you are binding this constraint. He's asking for this amount of utility. You give him exactly what he wants, not more. Now, if you look at this problem with limited liability, because you have limited liability, then it might be the case that it's better for you to give him actually a bit more than what he's been asking. Okay? And that's something that happens in the model that I've described and that already happened in Sannikov's model. Somehow you end up in a case when there is a trade-off between saying like, I'm going to give you more than what you want because with this it's going to be easier to give you incentives to work what I would like you to work. Because if I was giving you only your reservation utility, then I would have to pay more so that you would get the correct incentives, and the trade-off is better in this case. The second point that Sannikov has is concerned with when do you fire the agent. In his case, you fire the agent in two regimes. The first one is when certainty equivalent goes to 0. That's the bankruptcy. Things are pretty bad, and you cannot be sure that you will be able to pay him something more than 0. So when it reaches 0, you just stop and say, your salary is 0. Too bad. That's it. That's the end of the contract. Okay? Then there is a second possibility, which is when your employee is too good. If he's too good, then his reservation utility is going to be very high, and there is a point, and if you reach that point, then you tell him, no, that's not going to work, you cost me too much, so I'm going to give you what you would have now, and that's it. That's the end of the contract. Okay? So that would be something, so you can interpret this in two ways. Either this is some kind of weird golden parachute, because golden parachute would be paying him a lot in the case where you have bankruptcy. But here this is just, you're too good, you go out. Or you can interpret this by saying that you would have incentives to fire senior people and replace them by junior ones that you can pay less. Okay? That's one of the findings that he has. One of the good things about the way we are looking at the model is that it's actually, we can make it more general, we can have different utilities, and in our case, well, this second point where you would fire the agents, it actually disappears. I mean, there is a condition for this point to exist, and it's given by this, so it's something that concerns the risk aversions of the agents. And if you take the case where the principal is risk neutral, which is the case of Sannikov, then of course this condition is not satisfied, meaning that this point disappears. So in Sannikov's papers, he has power utility type. Now take the same model with exponential utility, and the conclusion that he has here completely disappears. So the point that we're making with this is somehow that probably you should be a bit more careful about the findings that you have here. If just changing the utility, which in any case, choosing power or exponential doesn't mean much because this is not extremely realistic, it changes completely the conclusions of the model. So that's the first thing. You can understand things like that in a more general setting. And more than that, let's say that you want to look at more general constraints. For instance, the one I was telling you about earlier. Of course, I lost the paper. If you want to have something like psi, for instance, yeah, this one is bad. What did I do with it? If you try to look at something like psi greater than 0, and let's say positive part of x capital T, because I mean, if I don't have any money anyway, this is going to be the end. Well, if you want to do this, it's not so complicated. The way I handled this was saying that the backward stochastic differential equation with terminal condition xi has to be greater than the one with terminal condition 0, and the solution to that one was always 0, so I had this constraint for every time t, that yt should be bigger than 0. Well, just do the same here. Look at the utility of an agent that will get exactly this as salary. That gives you another BSDE. It's Markovian, so you can always compute it by solving another PDE if you want. And this is going to give you constraints for Y, which are going to look like this. And this guy here will be a function of T and X capital T that you can compute not explicitly because you have to solve a PDE, but you have the constraint that you want. So now it gives you a more complicated problem with not only one state constraint, but two state constraints. This Y that you control with Z has to remain positive and has to be such that you're always less than this other function. And once you have something like that, you can write down the PDE and you can try to solve it. And really, I mean, I would say that this part is actually more interesting than the rest, because this is something that people know. This has been done in Sannikov. It's just another way to go to the same results, but it's actually the exact same ideas that you can have if you want to treat something like that. And this is something that I think is not present in the literature, and it makes it really easy. You just look at these BSDEs and you get stochastic control problem with state constraints in the end, and you can try to play with it. There is another way, I'm going to finish with that, to interpret this. Here what I'm really doing is, this is a kind of a terminal constraint, okay, because those are things that are working at time t, and because I know about BSDs, I'm using comparison theorem to transform them into state constraints. What you could also do is just say that you have to control Y by Z such that at terminal time, the value is between 0 and this. Then it would be kind of a stochastic target constraint if you go back to these problems that were introduced by Metesoner and Nizar. And for these problems, so that would be like stochastic control with stochastic target constraints. Then we can also write down AGB equations. This has been done in a paper by Bouchard, Elie, and Humbert. You can also play with this, and of course the PD that you would get by looking at this would be the same as this one because the problems are the same. But it might be that in some cases you could be better off by looking at the stochastic target constraints instead of this one. It really depends. Okay? But yeah, somehow what the message here is that this interpretation of the problem makes it extremely easy to handle any generalization that you can think of that would make the problem even more realistic. Of course, you have to play with the not so nice PDEs in the end, but that's not something you can avoid with this type of problems. And I think I'm done. Yeah. Yes.
Questions?
You might have said it and I might have missed it already. This X process, it's always a Brownian motion with a drift, or you?
In this case, so X, it's integral of alpha plus Brownian motion.
Yes.
So now it depends on what alpha is.
Yeah.
Now,
my question is, can you also like
make
the volatility depending on alpha? Or
of course.
Yes.
Okay, if I make the volatility depend on alpha, I can still make it. The story is more complicated, but I get a PD in the end, and that's the same story. Yeah, that works.
And the positivity, is this becoming more easier, I think, then, right? Is it?
I mean, if you make, for instance, instead of having X being kind of arithmetic Brownian motion, I take geometric Brownian motion, then it's easier. But I try to do the computations even in the easy case with geometric Brownian motion. You can do it, but it's not completely explicit. I think you get like the Laplace transform of exponential of minus a Gaussian. You have this function that comes up, and it makes the computation a bit harder, but yeah, that could help also.
Here I guess you mentioned it, but you are also taking the utility of the principal upon firing.
Yes.
Okay.
Because he's choosing when he fires, so you get utility when it's
On the
done.
other hand, the principal does not care about what he will get upon firing. He cares about what he will get in the end.
But after if you don't replace the agent, I know that Stéphane is working on a problem where when you fire him, you can actually replace him by someone else. Afterwards, then your X is just a Brownian motion, because the agent is no longer working, and if you're not doing anything, it's just a Brownian motion. So it's, if you have the value upon firing and you know the law of the tau when you're fired, then you can compute what happens afterwards.
You can, but you will not get the same utilities. I mean, the time that you're firing them will also be important, because you will have an uncontrolled process from that onwards.
Yes. Yeah, so the utility will be different, but it's mainly going to change the PDE that you have, right?
These target problems that you mentioned, is it the one that you enlarge the control with the probability of hitting the target? Is this?
So I think those are the ones where you do this Vollmer and Neukert quantile-edging. But this will be like, this is really probability 1, you want that you are in the target at the end. It's just that it's not just controlling the process so that it ends up in the target, it's that you are optimizing a criterion with the constraint that one of your variables has to end up in the target. It's like utility maximization with, you do utility maximization with the constraint of super replicating something. That's exactly the same type of problems.
Anything else? Okay, let's thank Dylan and all the speakers of today.